A future AI model crawls the web for training data. The problem is that a crawler often cannot reliably determine from the content alone which pages came from people and which came from earlier AI models. So the fear sounds reasonable. If models keep learning from model written copies, does the human signal get diluted until every new model becomes a blurrier copy of the last one? That can happen. But AI generated data is not one training method. To see when the danger is real, we have to build the feedback loop in miniature. Important. Start with a dataset drawn from people and the world. Train a model on it. Ask that model to generate a fresh dataset. Then discard the original and train the next model only on what its predecessor produced. Repeat this several times. This is recursive replacement. Each generation learns from a finite sample of the previous model's approximation. The loop no longer has direct contact with the distribution it was trying to learn. The failure begins in the shape of the data before the text becomes obviously bad. Suppose most examples are ordinary, while a few contain an unusual phrase, a minority dialect, a rare event, or an edge case. The model learns the common region best. When it generates a finite sample, common patterns appear again and again. Rare patterns have fewer chances to appear. Some are missed entirely, and any mistake that does get sampled can become part of the next model's training reality. The next generation is not copying files it once knew. It is estimating a distribution from a narrower, noisier sample. Repeat the replacement, and the losses compound. The center becomes overrepresented. The tails disappear first. Later, the whole distribution can drift away from the human data used at the start. This is the mechanism usually called model collapse. Shumailov and colleagues tested this recursive process with theory and controlled experiments across several kinds of generative models. Low probability events disappeared first. In the language model experiment, later OPT models performed worse on the original wiki text task. They concentrated on more probable sequences and accumulated errors inherited from earlier generations. The study demonstrated a real failure mode. Indiscriminate recursive replacement can corrupt the data generating process. One experimental choice matters here. Each generated dataset replaces the original data. Retaining a source data changes the result. Change just one thing. In the upper branch, each synthetic generation replaces the previous dataset. In the lower branch, the original data remains available and new synthetic samples are added alongside it. Now, a sampling miss is not permanent. The next model can still encounter the rare source example. A generated error also has to compete with data that did not come from the same model family. The loop has a reference point. In accumulation experiments, retaining real data avoided the collapse seen under replacement. The result is limited to the tested mixtures, and continually training on a growing archive costs compute. Within those limits, synthetic data did not make collapse inevitable. The construction of the loop mattered. The useful part of human data is not simply that a person typed it. Human data can contain observations, choices, disagreements, and rare cases that the current generator does not reproduce well. That means a small amount can sometimes change the result disproportionately. In one study of question answering and fact verification, adding as few as 125 human examples reliably improved models trained on entirely synthetic data. The results suggest that even a small, independent human sample can add useful information the synthetic set did not preserve. The ratio belongs to those tasks and model sizes. It is not a universal recipe. Keeping the source helps preserve coverage, but it does not tell us which new generated examples are actually worth learning from. To make synthetic data useful rather than merely less destructive, the loop needs a way to reject bad attempts. Instead of accepting the model's first output as training truth, generate several candidates and put a check between generation and learning. Failed candidates leave the loop. Accepted ones return as practice. Experiments on matrix eigenvalues and news summarization found that verification could keep a trained model from falling below the original generator under their operational definition of collapse, even when some verifiers were imperfect. That makes sense if the judgments correlate with the quality we care about. The check removes enough bad samples to improve the training distribution. But a verifier is not magic, and a second AI model is not automatically an independent source of truth. If generator and judge share the same blind spot, confident agreement can preserve the error. The strength of synthetic data depends on what the checker can actually know. The answer becomes easier when correctness can be constructed from rules outside the language model. Alpha geometry is a clean example. Its pipeline sampled random geometric premises, then used symbolic deduction to derive the statements reachable from them. Human design formal rules determine what followed from what. The system traced those valid derivations into theorem and proof training examples, building the synthetic curriculum from rule-valid deductions. Formal mathematics gives us an unusually exact judge. The same principle works in a more familiar place whenever an answer can be executed. A model can generate 100 solutions to a programming problem. A compiler can reject malformed code. Unit tests can reveal which behaviors fail. Known answer math problems can provide a similarly direct reward. Now, generation is paired with evidence. The failure says more than another model disliked this answer. It identifies a broken contract. A passing attempt can be selected as supervised training data, or the result can provide a reinforcement learning reward. This is why verifiable domains are so productive for synthetic curricula and reinforcement learning. Even here, the test covers only what somebody specified. Passing does not prove that the program is secure, useful, or correct in every situation. Most questions we care about cannot be reduced to a complete test suite. The loop can also receive new experience. A model proposes an action, an agent tries it, and the environment produces a consequence that was not sampled from the model's prose. In AutoRT, foundation models help propose and filter robot tasks, while a fleet collected tens of thousands of physical trials. The system was not fully autonomous self-improvement, and it was not a general success verifier. The model helped choose what experience to collect, but the observations and trajectories came from physical interaction rather than generated text. That produces new evidence. The pattern can extend to software tools, simulations, scientific instruments, or experiments where a system proposes an action, observes the result, and learns from it. Reality is slower, more expensive, and less tidy than generating text. These examples show how generated training material can be grounded. Web contamination remains unsolved. Some judgments cannot be reduced to pass or fail. A unit test cannot fully determine whether a story is original, advice is wise, a policy represents people fairly, or a scientific idea would matter if tested. People are not infallible either, but they can introduce goals, lived experience, disagreement, and information the current model family did not generate. In open-ended domains, compressing judgment into an AI evaluator may scale feedback, but it can also scale the evaluator's blind spots. Model collapse is a real concern when one model generates the lesson, supplies the answer, and becomes its own only judge. AI may generate more of its own training material, but it still needs tests, people, or the world to correct it. Next, we will look at continual learning. How can a model absorb new information without overwriting what it already knows? Subscribe if you want to follow that investigation.